So we talked a little bit about tuples, ways of grouping a fixed number of values where the things that you group together can have possibly different types. For example, combining a bool and an integer into a single value, a pair, and this was an example of such a function. You can also pull things, these tuples apart using pattern matching to pick out the components that you're interested in, or use them however you want to. So a few more quick examples. Here's an example of a specific triple consisting of an integer, 42, a bool, true, and a double. And here's a function which takes a triple of that shape and returns a pair of an integer and a double. And it does it by, in fact, ignoring the Boolean value completely and computing the integer to the power 2 and half of the double. It's not a meaningful function. It's just an example of something involving both a tuple on the input and on the output. One of the other types that we saw fairly early on was a string. I didn't really do very much with strings other than maybe join them together using an append operation. So you can take strings and append them together. We certainly saw that example earlier, so it's kind of obvious what that is. But what we're going to talk about now is the case of lists. So if tuples of sort of fixed size structures where the values have different types, you should think of lists as types representing structures where the number of elements can vary without changing the type, but the type of the components in the list are fixed. So you have lists of a fixed kind of thing, but the number of things in that list can vary. So used for different purposes than tuples, and maybe more interesting. So here's an example of how we write lists. We saw one example earlier. This is a list of strings, and let me just evaluate it. So list 1 is the list. Okay, let me just save that file and reload it down here. List 1 is this list here. Xchip, spam, spam, spam. So it's a list of strings because each one of these things is a string, and there's a list of them, and there are 5 of them in the list. But the type, in a similar way to the notation for types with tuples, sort of uses the same notation as you use to build tuples. The notation for types of lists uses the same square brackets that we can use to build lists. So the definition of the type of list 1 is that it's a list of string, because each element in the list is a string. And if we were to try and join this list with another list, the other list that we join it with would have to have the same type. Otherwise, we would get a type error. Okay, that's fine. So Haskell has a lot of syntactic sugar, you might say, things that are nice ways to write things which are actually a little bit more complex than they appear on the surface. And a string is one such example. So a string is a sequence of characters that we write between double quotes. So we can ask, what is the type of string 1? Well, string 1 is something where we declared the type as a string, so that's the type it is. But if we actually asked what is the type of this thing here, which we know is a string, what it would report is something a little bit different, namely that this is a list of char. So it turns out that lists of characters, here's a character S, a character P, and so on. This is a list of 3 characters. In fact, when we compute that, it is rendered, it is printed as what we are calling a string. So in fact, a list of characters and a string are the same thing, which maybe seems a little bit strange, but if we actually ask for information about string, what we see is that in fact it's an alias. That's what this is, a type synonym, as it's called in Haskell terminology. Basically, it's an alias for a list of characters. So whenever you see string, you can also read it as list of char, and whenever you see list of char, you can read it as a string. They're not different. They are the same thing. String is just another name for a list of char. Whereas char is a built-in thing. And it's got lots of complicated further information that we don't really need to get into just at the moment. Its type is not, it's not a primitive, it's a primitive type to Haskell. Okay, so we've seen that this is a syntactic sugar, a sort of nice way of writing down something which is actually a little bit more complex than it first seems. It's actually a list of individual characters. But it turns out that there is another bit of syntactic sugar that we're using in these examples, and it's this notation with square brackets. So this is very, very nice and quite natural for writing down strings, but it really is a kind of shorthand for something which is a bit more basic, a bit more primitive. So the basic fundamental building blocks of lists are not the square brackets and the commas here, but actually more basic operations than that. The first one is this thing. It looks like a little box when I write it like that. If I put a space in between, it looks a little bit more obvious. It's the empty list. So that thing is an empty list, and it's an empty list of whatever you need it to be. In fact, I can show you what the type is. What is the type of the empty list? It's a list of what? It's a list of, and it gives a small letter a. So this is a variable, a type variable. So this is polymorphism. It's basically saying this thing here can be a list of whatever you like. It doesn't matter what if you want it to be a list of elephants, it's a list of elephants. If you want it to be a list of int, then it can be a list of int, or a list of char. In other words, that could be a string, the empty string. It can be whatever you want it to be. So that's the first building block, the empty list. The other building block is a little operator which is pronounced cons, and it's the colon operator, and it's the operator for putting an element on the front of a list. So if I put 1 on the front of the empty list, I get a list with 1 element, and the list with 1 element is printed out in this way. If I put a 2 on the front of the list that I get by putting 1 on the front of the empty list. Now, fortunately, this is a right associative operator, so I don't need any extra brackets here. Then I get the 2 is the first element, that's the element on the front of the list, and it was on the front of the list with 1, followed by the empty list. So these are alternative notations for the same thing, and really you should think of the colon and the nil as being the kind of fundamental building blocks, and this notation as just being a nice sugar for writing lists in a nice way. And why do I bother mentioning all that? Because you'd much rather write this than write this, I'm sure. Well, the reason is because understanding the fundamental building blocks will be important when we define functions on lists. So I'm going to start by defining a function on lists which is not terribly interesting, a bit artificial, but we'll use this example, a list of food items, and summarize that list. And then I'll move on to more generic useful functions which will be defined by recursion. But I'm going to first start with a non-recursive example. And I'm going to start with an example which summarizes a list of strings by mentioning either special case when it's 1 item, when the list has 2 items, or when the list has no items or more than 2 items. So I'm not going to cover every possible case. The function, of course, will work in every case, but we'll only summarize up to 3 things in a given list. So I'm going to call it summary, and I'm going to start by defining what happens when you give it the empty list. So the summary of the empty list will just be the word nothing, and we're done. So the first equation to define the summary function will be nothing. And my summary function, let me just write in the type because I know what it's going to be. I'm going to take a list of strings and produce a single string that summarizes that list, capital S. Okay, summary. Let's look at a list with 1 item. So we're going to define a function that works on a list with 1 item. We're going to use pattern matching. The first pattern we used was the empty list. The next pattern we're going to use is a list with a single string in it. And that's the shape of a list with a single string in it. We use a small letter, that's the variable denoting the string itself that's in this list of strings. So the type of S, this little S here, will be a string. And I'm going to summarize by saying just appended to S. So I'm joining this string with this one. Okay, I can compile this even though the definition is not complete. It's compiled enough that I can apply the summary function to a single string with just, say, spam in it. And that will just summarize that as just spam. Okay, let's summarize 2 items. So what does a list with 2 items look like? Because if we apply this function to 2 items at the moment, then it will just give an error and give an exception. So here's a possible shape for a list with 2 items, S1 and S2. So this is a pattern. We're using pattern matching, and it matches any list which has exactly 2 items, 2 things in it. The first thing in the list will be called S1 and S2, and we're going to summarize that by saying S1 and S2. And I've got to append those together. So I'm using the append operation to join this list and this one and this one and this one. Actually, this is also a right associative operator, but it's associative, so it doesn't matter whether it's right associative or not. We can join a bunch of lists together. Okay, so we could summarize that now because we have a definition for that, and it's summarized as spam and spam. S1 matches this part of the list, and S2 matches this part of the list. Okay, this is going to get very tedious. How long are we going to go on for? Let's have a catch-all case. Let's suppose that we're trying to summarize a list that has more than 0 items, more than 1 item, more than 2 items. So we're going to have an equation for the rest. And we're going to summarize a list that we're going to write a pattern that matches every other case. So the way we do that is not to use this square bracket notation. That's only useful when we know exactly how many elements in the list there are. That allows us to build a list of a certain size. But when we don't know, we use, instead of using this square bracket notation, we use our notation that we introduced a little bit earlier, the cons operation. And the word cons here is a historical name coming from the Lisp programming language from the 1950s. So the catch-all case that will match any list with at least 2 elements will be to say the list starts with some string S, and then there's the rest of the string. So this pattern match looks quite different from the ones above. We need these brackets because we're using an operator here. This will match any list that starts with at least 1 value S, and this will match the rest of the list. So if the list has 10 elements, this will be the first element, and this will be the remaining 9 elements. Okay, so we're going to summarize by taking S, and we know that there's at least more than 1 more item in the list. So I'm going to summarize that by followed and ending with, and I'll write the next bit on the next line. And I want to take the last element of the list. Now I can't do that by pattern matching. So lists are structures which are accessed from the front. These are not doubly linked or double-ended lists. These are a fairly simple structure. We can access the front quickly and easily using pattern matching, but we can't access the end of the list in the same easy way. We'll need a function to do that, and that function won't be a simple function, it'll be a recursive function. We'll see how to define that in a minute, but there's a standard one called last. And we'll take the last element of the rest of the list. And we know that there will be a last element. This can't be an empty list, because if this was an empty list, this would be a list with 1 element in it. And we would have used this equation to summarize it. Okay, so let me put an extra space in there. Okay, so I have a definition that should work on something like list 1. So let's try that out. So let's take the summary of list 1. And we indeed get egg followed by a bunch of things and ending with whatever that last thing on the list was, namely spam.